Well, it's 3 o'clock in Denmark now. We have many other time zones joined, but so good day to all of you. It's great that you're joining to the third part of our webinar series. This webinar is titled Working Towards Net Zero. I'm Bastian. I'm sales engineer for Unisense Environment. I'll be moderating the session today. And all in all, we have signups of over 160 participants from all around the world. So truly from Australia, from China, through Europe, all the way to the United States. The whole world is joined in this webinar. So that's really fantastic. It shows how much traction this topic is getting globally. Just a quick look at our format today. We'll have 1.5 hours, and we have 3 great speakers for today, representing the leading Danish utilities and universities. Each of the presentations will be 15 minutes plus 5 minutes of Q&A. And after the presentations, we will go into a panel discussion where Mikkel Andersen, our own CTO, will join as well, and we'll get to discuss some broader questions. If you'd like to stay up to date on these type of events, please consider following us on LinkedIn. And if you want to continue the discussion one-to-one in person, you can find us very soon next week in Copenhagen at the IWA conference, and also later this year, end of September, if you're in North America, at the Los Angeles World Water Tech. So that's a quick intro to our program, and with just a few housekeeping things before we kick it off with the speakers. We all know that it's good practice to keep your camera off when you're not presenting. And please stay muted when you're not speaking, just to keep the background noise low. You can ask questions that you have in 2 different ways. You can either type them into the chat during the presentation, and then I will read them out afterwards to the presenter. Or you can choose to raise your hand. So you use the little raise hand symbol here, and then I will call you up to unmute your microphone and to give your question directly to the speaker. So both these ways will work, and we will try to answer all the questions. It depends, of course, how much we can answer in the 5 minutes. Just to let you know, everyone who signed up will get a recording of the session, a video recording, and also a PDF version of the slides. So there's no reason to take screenshots of anything. So that will be the way we do it. And with this, I think I can stop sharing here, and I'd like to introduce our first speaker. We will first have here Anders Lynggaard-Jensen today. Anders, if you want to take your camera on. Anders is from Aarhus Vand. He is the chief engineer for automation and process optimization. So he has more than 40 years of experience working with instrumentation and controls related to both water and wastewater. And today he's going to give a presentation on validating methods for nitrous oxide emission measurement. And I've heard that this presentation has not been given ever before, so it's a world premiere today. Very much looking forward to that, Anders. And with that, the floor is yours. Looking forward.
Thanks a lot. I'll try to share my screen.
Yep, that's perfect.
Okay, thanks. Yeah, what I'm trying to present today is a bit of practical experience with measuring nitrous oxide and some of the problems that we see, some of the pitfalls that we have, so that you all don't make the same mistakes as we have done. So so the overview is here that how we measure the off-gas flow, how do we measure nitrous oxide in off-gas, and how do we measure nitrous oxide in the activated sludge, and then the calculations that bind these things together. and then compare the measured and calculated things, and then a few concluding remarks. So let's start with the equipment for the off-gas measurement, which consists of a hood that you can see here on this slide. Can you all see my arrow?
Yes, we see that you will see a pointer. Yes.
Fine, good. So what we have here is a hood where we measure flow and we measure off gas, and we can see that it's placed located in an aeration field on an activated sludge tank, and this is in fact the EO wastewater treatment plant in Aarhus. And here we are just in measuring mode, so we are measuring both nitrous oxide and the flow coming up into that 1 square meter hood that we have here. If we look into the hood, then we can see that we are measuring the flow with a pressure difference, and we have some tubes here going to and from the nitrous oxide emission measurement, which that's an instrument which I'll present later. We can see the hood here when it's taken up in the crane, and from here we see the hood from the underside. We can see the small tubes here where we are sucking in the nitrous oxide mixture, and there's another one which you cannot really see here where we are pumping back so that we don't from the nitrous oxide measurement, so that we are not jeopardizing the flow measurement in the hood. So this is the setup for that, and when we are calibrating this, we have made some equipment here that we have, in fact, a diffuser here that we can put down here and put that under the hood. And we can see here that this diffuser pipe here, where we can see the diffuser is now under the hood there, so we can then put an airflow to that, and we measure that with a measurement here during the calibration, and we also have the airflow coming from the normal aeration system of the treatment plant, where we, for this tank, have 6 aeration fields, but we can close down all of them and then just use this pipe in order to take the flow that we want from this pipe. So that will be the calibration flow that we have there. At the same time, we can then measure what is the pressure difference in the hood. And if we do that, it looks like this. You can see here that we are regulating the flow that we are measuring, and we are then having a registration of the pressure difference. And then we can calibrate our off-gas flow using this equation. And we have done this several times. And this is some of the uncertainties that we really have in the system, is that having this pressure difference, which is a very small one. You can see in the start of the experiment here that there's a lot of noise on that, and then when we are taking control over the flow here, it's coming more stable, but still a little bit of noise here, even if we have a completely stable flow into the hood. But this is one of the important things, is that we really know the flow, otherwise we cannot calculate the emission correctly. Then we have the nitrous oxide measurement with the hood. This is an instrument from Thermo Scientific, which are measuring the infrared. We are having 2 calibration gases where we have a 200 ppm in pure nitrogen, and we have a pure nitrogen gas here, which we can put on the system here. We are having a gas pump where we're putting sample in. We're having a gas cooler. We're having a filter. So we are not getting anything into our instrument. We can put calibration gas on. We can put zero gas on. We're having an exhaust that is going back to the hood, and we are using about 1 liters per hour in the instrument, and the pump is giving about 5 liters per minute. It's per minute, 5 liters per minute, and so we are putting back that flow again, not to jeopardizing the flow in the hood, even if it's much smaller. And you can see that we are having different equipment here so that we can calibrate the system. And when we are doing that, we can see that we are coming up and down between the 0 and the 200. We have also been checking the linearity of the instruments, where we are having 2 flow meters, where we are having the span gas and the zero gas, and then we can mix them in different ratios, and so checking the linearity of the instruments. And when we are setting up everything and doing our real-time calculations, we are now having a system where we can measure the off-gas pressure difference, the flow. We are also having a filtered flow, which is the light blue, because we need to filter it. You can see how much noise we have from the pressure, which are going into the flow, and then we have the filtered flow. We are having the off-gas in ppm, which we recalculate into a concentration in milligrams per cubic meter, per normal cubic meter. And then we can, by multiplying those two figures, we can then get the emissions. So we are having the red one, which is our emission from our off-gas measurement, completely independent on anything else on the treatment plant. Then we are having the other system, which are the sensors which are installed at the treatment plant. And we can see here we have the aeration tanks at the wastewater treatment plant. We can see the flow going through. We have an anaerobic pre-tank here, and then we have the 4 aeration tanks. It's a plug flow system, and it's coming out here. The hood that we just have been seeing is sitting here, so it's in the inlet tank, and it's in the aeration field. We are measuring the nitrous oxide in these different locations here in the tanks, and we are having flow meters on each of the tanks, so we can see how much air we are putting into each of the tanks. Then I've just shown here that some of the measurements that we have been doing over a longer period, that's from the start of February this year until end of May, we can see that the nitrous oxide measurement in the activated sludge is changing a lot in this period. So we are in fact having different periods here of how much it, and it's not just because that we are experimenting a lot with the different controls. It's simply changed with the same control. We simply changed level around April month. So it seems that we had some other population going up there. Anyway, it doesn't matter if we are here comparing how good we are to measure the nitrous oxide emissions. So this has nothing to do with our control experiments, which we can come back to some presentations later. So the nitrous oxide sensor, we are having 4 of those, and we are having 2 transmitters, and they're sitting there, and they're just down in the activated sludge. We are having the flow meters that we are using for each in the aeration manifolds are thermal gas mass flow meters that we're using there. Then one of the really difficult things here is when we are now starting to compare our results through the calculations is that how much is the aerated area? How much area is covered by the off-gas meter, so saying that, well, that has 1 square meter, but how many square meters are feeding or evaporating from the tank? And if we try to calculate that from the cluster of diffusers, then we are having 45 square meters of the area of the diffusers. But when we look at the surface and try to measure, try to estimate what is the area there, we are then getting approximately 65 square meters. And then, of course, that area is quite important in the calculations, and also the aerated volume and the non-aerated volume are quite important in the calculations. And if we see that we can, at the surface, in fact, see 1/3 more than what we are having in the diffuser area, then the volume maybe should be calculated from the mean between these 2 areas here, because that we're having a rhombic figure there for the volume. So there's something to work with there. But this area is around total 390 square meters. If we look at the plot of the airflow to the tank, measured by the normal flow meters and our off-gas flow, we can see that we in fact are having 393, which is in fact a good idea of how those square meters are fitting together. So what we were estimating 390, and if we take to fit all the measurements here every minute, then we are getting 393, so not too bad. We are doing a calculation train so we can follow all this in real time, and I don't know if you know the real way of calculating this from different papers in the literature, but in fact the green ones here, that's the raw measurements. So we need the tank level, we need an airflow, we need a temperature, we need a nitrous oxide, and then we're having some correction here as we are trying to calibrate for any drift on this sensor. We are filtering those, we are calculating the Henry's constant, we are calculating KLA and temperature compensated, we are calculating emissions and so on. So all this calculation train is running every minute, so that we in fact are doing each of those blue square here is in fact a software sensor. So if we look at how we calculate it, you can see this afterwards. I will not use any time for looking at these, but this is the calculation of the KLA for nitrous oxide, and we are doing exactly that in the system every minute. We have the calculation of Henry's constant, which we also do exactly like this every minute. So we are then having these curves so that we can follow in real time. So we are having you can see the airflow, which we are filtering. The light blue is the airflow, and this is from the wastewater treatment plant. This has nothing to do with the off-gas measurements. We can see Henry's constant here and the temperature, and also the KLA and the temperature compensated KLA. So that's that part of the calculation train that we can follow on this curve. Then from that we can calculate the specific nitrous oxide emissions, and we are calculating that also from literature here, and the aerated zones is given by this, and the non-aerated zones by this equation, and you can look at that afterwards in the slides that you have in the PDF. And if we look at that, then we can see at this curve we are having, firstly we have the nitrous oxide measurement, and then we are having the specific nitrous oxide emission, and then the oxide emission from the aerated and the non-aerated volume, the exact emission from that. And what you can see here is that the violet ones are the specific ones, and the more red ones are in fact the emission. And as you can see here, we have from the non-aerated area, we are having 10 to 15% of what is here. Now you could wonder why are we having this peak here, but this is exactly we are running with a constant air rate here, a constant flow rate, which we could see here, just to see what will happen if we are running with a constant flow rate. Here we are having our control of the system, and we're also having that here. But here we set it to give a constant flow rate, so we will see what will happen with a varying load of ammonia through the day. And so, in fact, with a constant flow, this curve is an expression of how much nitrous oxide are formed just by varying the ammonia load into the system. And we are having that because then we are having a good range which we can use for our calibrations. Then if we compare the emission that we measure with the off-gas, which we have used at the same time with this, we are having the same period here. Then we can see that from the off-gas measurement, we are having the violet curve here, which are not too bad if we are at lower figures. And if we are at higher figures, then it overestimates, the calculation overestimates the emission that we in fact are measuring. in the lower one here, we are trying we are taking a accumulated value over the day, and we can see here that here we can the violet is still the off-gas measurement, but here we can see the from the non-aerated volume, we can see from the aerated volume from the tank, and here's the total. So again, we can see that the non-aerated contribution is, well, it's not the bigger one, but it is significant. Conclusions. If we take for the whole period that we have been using here, that's about 2 months, and are taking the daily values of the nitrogen oxide emissions from the off-gas measurements and from the tank and the wastewater treatment plant itself, then we are getting this curve. So what we can see is that it is not too bad when we are at the lower figures, but it overestimates when we are coming up in the higher figures. So, and some of so what can we do about that? Well, we'll try to make some conclusions. So working with the hood itself, it is difficult to measure off-gas flow precisely, because the hood is, if we are having a lot of air going into the tank, it's tipping, and it's, well, it's, so the pressure is in fact having a lot of noise there, because it's very unstable in the water. It's not that anything is coming from the sides, but it's going up and down very quickly, so we are getting noise on that. However, the off-gas nitrous oxide that we are measuring is quite stable. When we are comparing the emissions, well, it is, as I showed you, the aerated area and volume is difficult to estimate, and that is really an important parameter in the calculation. Calculations overestimate at higher nitrous oxide, at least when the higher nitrous oxide measurements in the activated sludge. And the calculated emission from the non-aerated volume is constituting around 10 to 15% of the total. And for the further work, as I would say, we also have to find a way to check what is the non-aerated contribution, because we have not been checking that. We have been running with air all the time. Anyway, for further work is that we want to work a little bit with uncertainties of our estimates for the existing formulas, and because then we think that there's a lot to do with at least with the aerated area and the volume. And also, we have not used any alpha parameter in the KLA correction here. It is a pure KLA, so could be that a little bit of correction term on that would bring things to better. So it will show more what we are finding in the real world. And then we like to introduce some correcting terms, or maybe suggest a new formula in the further work. And I hope this can give you an idea of how easy or not easy it is to try to validate the measurements. Thank you.
Thanks very much, Anders, for the fascinating presentation, and great to see the work that is going on so close here at AO Treatment Plant. And especially, working together on pushing, the accuracy of what we can do in terms of calculations. It just came to mind that all these basic KLA and Henry's constant calculations, they are of course also part of our compendium that we have with our setup. We can share that with all the participants of the webinar, so you have a baseline of these calculations and the literature that they come from. But we have a few questions, and we have a little time to answer them. So I'll just pick them out for you. We have one from Oliver, who is asking, how do you approximate airflow out of the aeration lanes directly? Do you simply divide it by surface area, or do you account for gas uptake into the solution, etc.?
I'm just taking it from the flow.
Yeah.
To the tank. So
it's a matter of having as many flow meters as you showed in your
and we have a flow
graph.
meter for each tank.
Yeah, and this is a very special situation, of course.
Well, we are using our controls because the best way of controlling, in fact, to control the flow.
Yeah, absolutely. Yeah, and that's a discussion we should go into later on in the panel discussion as well on the controls. For now, another question is from wastewater treatment in Cologne, whether you think it is helpful to use the KLA value that is achieved by a guarantee run or the first run that you would have with a new air diffuser when it is being installed, to use that value for your calculations. What would you think about that?
Well, you need then to make a ratio onto nitrous oxide. In fact, one of the methods that has been presented is in fact to take a ratio between the oxygen KLA and the nitrous oxide KLA. Well, it could be an idea, but anyway, it's we have been using this one.
Yeah. Very practical questions. Which brand of flow meters do you use?
Which of them? The one in the treatment plant. That's coming from a company called Sierra.
Okay. And then we have a bit of a more generic question, which probably also we can go into later. Whether you think maintaining a DO at, for example, 2 milligram per liter at a high level would limit the N2O emission peaks.
No, it will not.
Without taking energy into account.
It will not.
No, because of course both high DO and low DO can be triggering.
Yeah. It depends on well, as far as we can see, well, the emission, well, that's much slower than denitrification, in fact. And if you can get simultaneous nitrification, denitrification, where you're running with low DOs, and if you can sustain that simultaneous nitrification, denitrification, you can get rid of your nitrous oxide. This is what we are seeing with the work that we are doing right now. Yeah,
and we would love to see that in a further presentation. I think, as you mentioned, that would be great. I have a last question to round it off. Maybe just because you were also closely seeing and involved in the development of the liquid sensor from the beginning on, and now you have a lot of experience with the hood as well. If you can just give some a practical comparison maybe of what it is to work with these equipments.
Well, if we can get the calculations right, it is much easier to use the sensor in the Unisense sensor, in fact. But that's the whole story. If we cannot get that calculation correct, then we have a problem. But if we can, it's much easier to work with. The hood is not easy to work with.
Yeah. So I think it's a balance between the practicality and being as precise as possible, which is of course.
For the controls we're doing, it is fine with the calculations that we're doing right now, and with the sensor placed in the activated sludge, because we want to have it in each tank, and we are using that in our controls. So if we should have it in each tank, well, we couldn't use our time for anything else than just maintaining those hoods.
Yeah, indeed. Yeah. Okay, well, we've reached the end of the time slot. Thanks very, very much for the discussion and for your presentation. If you can just unshare your screen, and then I will call up the next speaker, which will be Maria Faragò. And just a quick introduction to Maria. Hi, great to have you here. She's right now still a PhD fellow at DTU Sustain. In her project, she's been working with the 3 biggest Danish utilities, helping them to understand their path to resource recovery and net zero emissions. And I've heard that just in October, right after finishing her thesis, she will start a job with Rambøll. So congratulations on that great next step. But today, she will present part of her work in her PhD, and very much looking forward to that. Floor is yours, Maria.
Thank you. Yeah. Okay. Yes, I can. So yeah, today I'm actually going to present a topic that is published a journal. So it's part of my first scientific article and of my PhD. So I'll focus primarily on life cycle assessment of water resource recovery facility in Copenhagen, and particularly I will focus on the role of the N2O emissions in this type of assessments. And how come do we need to look at N2O in wastewater treatment? Well, basically, in wastewater treatment in Denmark contributes to 10% of the total waste sector's greenhouse gas emissions, and N2O emissions from nitrification and denitrification are a major source of greenhouse gas emissions from wastewater. But we also know that wastewater has been actually considered also as a resource in water resource recovery facilities, where we can actually recover phosphorus, for example. But in Denmark, we also have plants, approximately 51 plants, that also produce biogas and then energy. So we have this double phase as such of wastewater treatment. From one side, in future water resource recovery facilities, we need to reduce our direct emissions, especially of N2O and methane emissions, but also on the other side, in order to achieve climate neutral plants, we also need to recover as much resources as possible, and we need to do it sustainably. So by doing so, we need to make sure that all this process happen in a very sustainable way, and that means also quantify a broad range of environmental impacts. So today I'll focus on a specific case study. I'll focus on a plant in Copenhagen that is called Avedøre wastewater treatment plant. Avedøre has a capacity of 400,000 PE and also produces energy. The future strategy for this plant is that the wastewater operator, Biofos, wants to retrofit this plant to a water resource recovery facility in 2025. And this is basically aligned with their goals. The goals of Biofos are reducing CO2 emissions, recovering more energy, and recovering more nutrients and other resources. So they would like to basically achieve climate neutrality or being even climate positive. But in 2016, actually, Biofos applied for fundings to the Danish APA, and they applied for fundings in order to convert their retrofit their existing plant to Faragò, that basically in Danish stands for Water Resource Recovery Facility. So they have obtained fundings in order to retrofit the plant with a lot of technological advances that include, for example, biogas upgrading, phosphorus recovery, ANAMOX implementation, carbon harvesting, and also a big part of this is implementing sensors and real-time monitoring and control for reducing N2O emissions. So unfortunately today I cannot go through all these technologies, but my focus will be on the Unison sensors and how they have been applied basically in the plant in order to reduce N2O emissions. And also I will mention the ANAMOX plant. We do not have a real implementation of this plant, and probably it's not going to be implemented, but it was part of the project. And the reason why I would like to mention it is because we also have a risk by implementing this plant. There is also a risk that we might increase the N2O emissions. So when we have these big systems, we always need to look at it from a holistic perspective. So we have to ask, is this actually a new system with all this new technology sustainable? And how can we quantify the sustainability? I mean, it's not just enough to say we want to reduce emission. It's not just enough to say we have to recover phosphorus. I mean, it's not because we are implementing high level of circularity that we are actually sustainable. So in order to quantify the sustainability and therefore a broad range of environmental impacts, we need to calculate these impacts. And specifically in my PhD, I combined both economic assessments with environmental impact assessments. And according to the methodology I used, the eco-efficiency methodology, when we perform environmental impact assessments, that need to be done with a life cycle assessment. So it's a must in this type of assessments. And basically in this specific case study on the Faragò project, we also based our evaluation on mass and energy balances. And also we calculated the CO2 abatement costs. What is the goal? Basically, we want to address whether the new technological advances are improving the environmental performance of the system, of the new plant, compared to the existing plant, as well as if they are actually increasing the economic value compared to the existing plant. So that is the goal. But today, actually, I'll focus primarily on the environmental impact assessment and the life cycle assessment. And given that I didn't know about if you actually had a background within LCA, then I thought to provide a brief introduction to LCA. So the life cycle assessment basically enables us to perform a holistic environmental impact assessment from cradle to grave, where we make an inventory of all the material consumption and emissions along the life cycle of the system, in our case, a treatment plant. So we go from material generation to final dismantling and disposal. So we make an inventory of all this input, including transportation, but also very important, all the direct emissions to air, like the N2O, emissions to soil, emission to water. And because we want to assess a water resource recovery facility, we also know that we have co-products, and these co-products can be energy, for example, biomethane, heat recovery, but they can also be it can also be just fertilizer, so phosphate fertilizer. So each time we are recovering a product and we are exporting this product, we are basically substituting or avoiding impacts of other conventional production of this co-product. So that is also very important. With the LCA, what we do is to move our decision support tool from being only focused on carbon footprint to a very holistic tool, where we basically not only have the climate perspective, but also we look at another broad range of environmental impacts. For example, resource depletion, for example, eutrophication or ecotoxicity. And I told you we need to make this inventory that you probably know from the carbon footprint assessment, and we need to model our system. We need to model our plants. So in my university, we use the software ISTEC, and in the end, after we model or input all the inputs and outputs, then we get this environmental profile that tells us the performance of the plant in different types of configurations. So here you can see you do not only focus on climate change, but maybe you might have other types of problems in other categories, for example. Specifically on the N2O sensors. So I told you in this Faragò project, it's a very big project, very interesting. The sensors actually are a small part of it in terms of equipment, but it was very important to understand how much data we need in order to make an assessment of the and understand the impacts of the N2O sensors. So also on the equipment, that means that we do not only take the benefits of the sensors, that enables us to perform real-time measurement and control, and therefore reduce the emissions, the N2O emissions, but we are also looking at potential background impacts from the material. So we looked into the material transportation, but very relevant is the lifetime, because even though this component is very small compared to other components, but still it's important to understand at the early stage of the design and planning the lifetime of these components, because for example, if we look at the sensor head, this needs to be replaced every 6 months, the sensor body every 5 years. But then when we define our time horizon, for example, is 50 years, then we need to understand how many times we need to replace these components. So in the end, actually, this component, the sensors compared to other technologies, indeed did not impact the system or did not provide additional environmental impacts compared to other technologies, but it was still good to include it in a life cycle perspective. And these are the kind of inputs that we need for performing an LCA assessment. So given that the project is very big, I would like to guide you through the alternatives that I have defined in order to perform this evaluation. So the baseline plant is a conventional plant. We have activated sludge system, we have anaerobic digestion, dewatering, drying and incineration, and then biogas upgrading that in the baseline scenario we assume being performed with amine scrubbing. So in this baseline, therefore, we do not have real-time measurement and control of our N2O emissions from the activated sludge. When we retrofit the plant to a water resource recovery facility, as you can see, we are touching a lot of processes. So the boxes marked in pink, they represent the novel technologies in this water resource recovery facility. And specifically today, I will look at the effect of the N2O sensors in the activated sludge and the real-time measurement and control. And also a little bit, I'll touch upon the ANAMOX and the potential effect that the ANAMOX has on increasing actually the N2O emissions. So as you can see in our water resource recovery facility, the complexity increases, and therefore you need to make this, you need to understand the contribution of the different processes out of the net, out of the total emissions in the system. I would like you to focus on primarily on 3 alternatives: the baseline, the RF N2O, that is basically the baseline plus the real-time measurement and control performed with the sensors, and then the final one, where we have all the technologies included in the Varga project plus the ANAMOX. So in the beginning, I told you that I based my assessment on mass balance and energy balance. I just would like to give you some figures in relation to the N2O. So when we look at the baseline performance, the estimated emission factor was 2.6%, while when they implemented the control with the sensors and they made some measurement campaigns where they implemented some types of controls on the DO level, then they could get down these emission factors to 1.6%. And that is even actually a very conservative estimation, because I know that from the latest results, they could even get higher reduction than what I have included in this study. With ANAMOX, so if we look at the last alternative compared to the others, then we see a slight increase of N2O, and that is basically based on literature studies. So there are no measurements in this alternative. But even though the percentage of contribution, the emission factor is very low, it's 2.6%, 1.6%. Actually, you know that it contributes a lot to the climate change, to the carbon footprint of the entire plant. So if we look at the major contribution of the positive emission in this plant, these are coming from the N2O. So it's very, very important that we kind of bring down these emissions. when we implement the control, the real-time measurement and control, then we achieve a very high or higher reduction compared to other technology. And it's, in this case, a very conservative estimate is approximately 35%. When we look at the ANAMOX, we could see that from literature, we could see that one of the downsides of the ANAMOX is actually that may increase the N2O. So there is a slight increase compared to the other alternative. Overall, I have to say that just by actually looking at the direct emission, you can bring a lot of, you can reduce a lot of CO2 equivalents. So if you can bring down the N2O and the methane emission, that would be a very good thing for your plant. Also because the other technology, for example, when we perform the upgrading, therefore we are substituting the natural gas production, they are avoiding impacts. They are not reducing the impacts as such. I mean, so that means basically that these technologies rely on the background energy mix, for example, or gas mix, while your direct emissions are on your control. I told you that LCA is not only carbon footprint, but we also, with the sensors, by also looking at the life cycle of the sensor, of the equipment, we also looked at the effects, the potential drawbacks of having, in other categories. So when we look at the other categories, for example, the resource depletion, the mineral resource depletion, we can see that actually we are not increasing the impacts at all. Actually, the sensors do not increase the impacts in the other categories. It's just below 0.4% increase. So it's actually very good also in the other environmental categories. The other two environmental impacts impact categories that are very relevant for a treatment plant are freshwater eutrophication and marine eutrophication. The reason why I want to mention it is because ADDA discharges into marine water, so very relevant is the marine eutrophication. Most of the impacts are coming from the direct discharge of the effluent. And I want to highlight the fact that even though the ANAMOX was slightly increasing, the N2O will still provide a beneficial effect at the effluent. So as you can see, you are increasing some impacts in some categories, but we are decreasing impacts in other categories. And these types of trade-offs, these are able to be made clear in an LCA assessment, as well as when we look at other technology, they might sound very environmentally friendly when we look at the climate, but then when we look at the other categories, they might increase the impacts. Just a little bit about the economic results, the financial results. I have calculated the CO2 abatement costs, and we have performed this economic assessment actually. And just by looking at the cost and how much CO2 is reduced, we could calculate that the cost for implementing the abatement cost of real-time monitoring and control is about €2 per ton CO2 equivalent avoided. And what I would like to say is that this technology actually is quite cheap compared to other technologies and can also bring down, take down a lot of N2O emissions and therefore CO2 equivalent. We also tried to internalize the CO2 equivalent with a CO2 equivalent allowance price. And at that time, in 2019, when I performed the study, it was very low. It was about €25 per ton. But now if I had to actually remake this assessment, if I have to make this assessment with the Danish carbon tax, maybe this assessment would look different. And probably the value added of all these technologies, including the real-time monitoring and control, would be much higher than the baseline. So in conclusion, I would like to say that just by only focusing at the real-time measurement and control, I can say that this technology compared to others achieved the highest reduction in direct CO2 equivalent emissions with no significant impacts in other environmental categories. Also, they were the cheapest solution. And what I want to say is that the wastewater operators are in control of this, of reducing the direct N2O emissions, also called Scope 1 emissions in greenhouse gas accounting. And also they are responsible and they are in control of the equipment. So what equipments they can actually use and how many. So they can actually, if they perform this type of assessment, they can actually find out what is a very good technology, both to bring down the direct emission, but also to reduce Scope 3 emission. And there is a lot of discussion about the energy and the avoided impacts. What I want to say is that it's important to inventorize them, of course, but this is not depending on them. The background energy mix is outside the wastewater operator's control. And therefore, if your background energy mix is not based, for example, anymore on renewable, then you might end up increasing your CO2 equivalent emissions anyway. On the other side, I would like to highlight that even when you have high share of renewable, still, if you only look at the climate, you are not able to get the full picture, because wind-based electricity, for example, might reduce the climate, but potentially might increase the impacts of other LCA categories. And therefore, I suggest to evaluate technological advances in a water resource recovery facility with an LCA perspective, and because it's basically able to capture impacts that are not captured by carbon footprints alone, and also it's able to highlight trade-offs as such. So I hope you could understand, you could follow, because it's a lot of information. But if you have any questions, you're welcome to ask now or afterwards. These are my contact details. So thank you for today. And I would like to actually say thank you to all my project partners, Biofos, Unisens, Enviden, and also Van Centersud and Orosven, and the Danish Environmental Protection Agency for funding the project. Thanks a lot.
And many thanks to you for giving this great overview. Very special plant, very fascinating project, the Faragò project. So yeah, it must have been fascinating to work on that. Just to mention to people who will be in Copenhagen next week, on Tuesday there'll be a technical tour of the whole Faragò project across the plant, so you can still sign up to that, as far as I'm aware. We're a bit short on time here, but we have time for one question, which is from Michael Gerardo. He's asking about the approaches, technologies that were used for the real-time control of the N2O, and what parameters were used in that process control. So perhaps the question can also be formulated: how did you get to that relatively conservative figure of 35% reduction through N2O process control?
Yeah. That's a good question, and I expected actually. Well, I mean, I have to say that I didn't perform the measurements, so all the results. I mean, I relied on results from other studies and from real time measurements and control strategies that were implemented. Actually, in this study, Chen et al. 2019, I provided a reference, and basically, in this case, they reduced the DO level by 0.5 milligram per liter, and that's basically what I knew about the process. And also, I think they looked into the anoxic phase, the length of the anoxic phase. So I relied on results reported to me by the people who have made these measurements and implemented this control. So that's how I came with the number. Yeah. And I think over the campaign period, they could achieve a range of reduction between, I think we said between 30 and 60%. So then we used 40% just to be on the conservative side, because actually when we make this assessment, sometimes we are not sure if we have not validated fully, then we need to be careful on what number we put, also to avoid greenwashing and so on. Yeah, but I have the reference to the study. It's published.
Yeah. Fantastic. And maybe even this is a perfect handover to our next speaker, to Dines, who I'm sure was deeply involved in that. So thanks again very much, Maria.
Thanks to you.
And let me just quickly introduce Dines. He's head of R&D for Biophos, so the biggest utility in Denmark. And he'll be presenting a bigger study of EU wastewater treatment plant greenhouse gas emissions. But of course, feel free to just comment on what was asked before. And very much looking forward to the presentation, Dines.
Thank you. Yeah, I was just tripping a little bit because I think Mikkel maybe want to answer the question in the panel afterwards, because he knows most about what we did control-wise.
We will take up that as the first question.
Yeah. So I think that's better that I start talking about it, because I hurried up and took a picture of the wastewater treatment plant behind me, because to show you that that's where I work. That's my office there also. So I've been heading the Waga project with some of my colleagues, and we are looking forward to show it on Tuesday. But unfortunately, the tour is already full. But good for those who are on it. Yeah. But that's not my topic today. I'm going to sort of broaden the perspective even more than we've done, than Maria has done. Anna started in the very concrete about the measurements, and then Maria has talked about this LCA and Denmark. And I'm going to talk about, let me see if I can. I'm going to talk about Europe in total, because I've been involved in a study initiated by European Commission Joint Research Center on what is the consequence for all European plants if we try to look into greenhouse gas emissions in different angles, in different type of plants and different way of operating them, and what do we calculate. So we've been looking at this study. Are you seeing my total presentation? Yes, you are. I hope you are. Not presentation mode.
It looks fine. Yeah, perfect.
Okay. So this paper was produced this year, and you can, if you're interested in this, when I've been talking about it, it's in the Science of Total Environment. I'm going to tell you some of the conclusions here from this paper. The idea was to look at the whole database of European plants. There's a database with 27,000 plants where we know what type it is, we know what how big it is, and so on, and then we can actually calculate with some literature. This is also based on literature, on also reference from experiments, not measurements directly, but literature on all the plants, and then to calculate, make a total big spreadsheet that can calculate all this from all the European plants. And then we are looking at different emissions. Of course, the direct emissions are shown on this slide. Where we take a standard wastewater treatment plant, where you have the emission of methane from the primary sedimentation, nitrous oxide, and methane from the activated sludge, the biological part here. And then we have, of course, something from the effluent in the receiving body. We have methane coming from different part of the sludge treatment train, and that's the direct emissions. But the assessment also included other emissions. So first of all, if you say look at this number one, life cycle emissions, like Maria has just been talking about, but this is from infrastructure. So all the concrete and the steels was included as basic values. Emissions of dissolved, number two, emissions of dissolved methane in the sewer networks. So we looked also at standard values from the sewer networks. Direct emissions from what I just showed you on the previous slide, the N2O and the methane from the treatment process. And then for emissions of COD and nitrogen in the effluents. Also, that was on the slide also previously. And then the indirect emissions, as Maria also touched before, when we generate electricity, we have this, so that's into the paper as well, and then also the emission credits, so the ones that are actually point the other way, the good ones, when we export biomethane, for instance. And the scenarios treated in the paper are split up in different plant sizes and types. So you have the sizes. Typically, it's important for the next figure I'm going to show you if you haven't seen before. The sizes are above 100,000. All the plants that are more than 100,000 PE. Then the ones that are between 100,000 and 30,000 PE, ones between 30,000 and 5,000 PE, and also smaller than that. And the sludge stabilization method has also been looked at. Is it anaerobic digestion or is it simultaneous aerobic sludge stabilization, the SAS? And the removal degree, what kind of treatment do we have? Levels of treatment, only COD removal, CODP removal, nitrification, this one, and nitrification plus phosphorus total nitrification, and so different levels of treatment also. So the calculation of the greenhouse gas emission was based on literature constants. Now this figure is, oh God, it's small on my screen. Sorry, hopefully it's bigger on your screen. This is a quite information-dense figure, so I'm just going to spend a little more time on trying to explain this. What you see are on the x-axis, you can see the number. All the points start with a number from 1 to 4. So this is the different categories of plants. You can also see this that this is sizes. So to the left you have the big plants, or the one that starts with 1 in the legend. That's the big plant above 100,000. And then until it starts with number 2, then you have the 30,000 or 100,000 to 30,000, and so on. So the farther you go right, you have the smaller plants. But and then you have the different colors in the figure that you can see. The green is basically the nitrous oxide. The blue is basically the methane, and the gray is the infrastructure, so the concrete and the steel. And the red is the burden from the electricity. And you have some that goes below 0 in the bottom, which is the credit you get when you produce electricity. So what you see here is basically the result. I will not talk about the lines there. It's not so important for this. But what you can see is that, of course, if you remove more, the best treatment when you remove both phosphorus and total nitrogen removal, you have the lowest. The assumption here is that the nitrous oxide emission is very low when you have this full treatment, and also the simultaneous aerobic sludge stabilization. So that has the greatest impact, actually the green part of the column, that is the nitrous oxide. So it's very important, basically it's very important what we do with the nitrous oxide in our wastewater treatment plants. That's the main message from this, I think. We have just a little other dimension for this. If you take the total, if you notice that the figure before was yeah, I have to go back. The unit of this, the y-axis is a kilogram per PE per year. So this is per personal equivalent, and we are in the area of 50 to 120 kilograms of CO2 on total equivalents. That is. Here we have summed up the total emissions. So you can see it in tons and in million tons actually per year for total EU, and the different scenarios that you are actually able to do. Of course, this work is also going to be a part of the work that's going into the new European Urban Wastewater Directive. So it forms databases for what to do. So here we have the sum for the whole EU. What you see below this, the dashed line, is the infrastructure. That's the same for all of these. And then we have, on top of this, you have the different scenarios that you could imagine for doing something about this emission. The best one here is total nitrogen removal and oh, do you only see the title slide? I'm sorry about that. Somebody should have told me before.
No, it's not an issue for me, at least. I see the one you're talking about.
Oh, okay. Yes. I hope most people see what is with the headline total GHG emission EU. And
yes, that. Absolutely. Yeah. Maybe it's a frozen computer. It's some others. Yeah, I see some thumbs up, so that seems to be fine. Okay. Yeah.
Good. So what you see here is the different levels. What is going between somewhere around the current situation. What we're doing in EU now is 35 million tons of CO2 per year from all the wastewater treatment plants in the EU. And we could actually reduce that to somewhere in the area of 25, or even down here somewhere in 22 million tons. So it's quite a heavy reduction actually. Just when you look at what you can be done in the operations side, of course the infrastructure side is a little more difficult to do something about. I just read today that we have a Danish concrete factory that can make concrete pipes that have the 50% CO2 footprint compared to other ones. So I think that's very interesting news. So that will be able to reduce this very much. But I think it's still interesting. You can see that this is, you can do a lot by improving the treatment in the wastewater treatment plant, also at the same time reducing the GHG emissions. The conclusions from the paper here is that I told you the emissions is somewhere in the area of 50 to 125 kilograms of CO2 per PE per year. So you could compare that to what else we emit when we take the plane ride to Asia or whatever. So it's not so much, but still it's important. The primary sources for this is the nitrous oxide and power. Methane is second. Low or zero footprint from power is important and is expected. It's actually in this some of these scenarios I showed you was you were expecting to have electricity with no CO2 footprint in 2050. Full nitrogen removal and methane recovery are important tools in the reduction of carbon footprint. So we have to that's actually an argument for improving the whole level of nitrogen removal in the EU. Yeah. And I think what was not mentioned so much in the paper, it is mentioned, but what we see also, as you have seen today, also from Anders' presentation, that the NGO emissions are far more dynamic than a constant factor can describe. So we really need to measure the nitrous oxide, which I know that Unisense will be happy to for this message, but that's a fact. You have to measure the nitrous oxide in your plant to control it and to be able to know where you are. And we see a heavy variation all over the season, also more in summer than winter and so on. So it's very important. I think that's about my presentation, Bastian.
Yes, thank you very much, Dinas, for this great overview. And well, thank you for your work in putting this together with the authors, and doing the bit at the EU to push forward to the common goal to reduce emissions, of course. One question that is coming up for me, since we're talking at this more broader scale, EU level, maybe even globally, since I would just like to pose that question to you. What do you think is the best driver to actually make greenhouse gas reductions a reality? Of course, Denmark has a special situation, but what would you propose for other countries? Maybe you can elaborate a little.
The short answer is money.
Yes.
No, but I think legislation or a CO2. I think the world needs CO2. What do you call it? A tax for CO2. If we get that, we are planning to have that in Denmark. I think it should be everywhere. And of course, if you have a CO2 tax which includes the nitrous oxide emission, then you would be motivated to do something about it. And as Maria actually showed, it's quite cheap per kilo of a ton CO2 to do this, especially when you just install the sensors and control it. So I think that we need legislation and we need a CO2 tax.
Yeah. I'm just checking. I don't see any questions in the chat right now. So I think with that we can also open up the discussion then to the whole group. So I'd like to invite all the other speakers. Thanks again very much, Dinas, to have the panel discussion. Take it maybe a little bit broader, or zoom out, or highlight some things that were discussed in the previous presentations. So we started out with a lot of questions around, and of course that's the thing that everybody is interested in, how to reduce the N2O emissions, what to do with the measurement data. So maybe if we take it backwards, the case of Biophos that we're talking about at Avedøre, maybe Mikkel, you could comment a little bit on that, what has been done and how much you can share and how much will be shared sooner. But just to give some hints also from your background, what you think works best in terms of mitigation.
Yeah, so originally in this Faragò project, we had elaborated plans in terms of doing mitigation, including working with the anammoxide stream mitigation and so. But along came COVID-19 as well, so our sort of research program was diminished. But one of the things that we actually spent time on was looking at literature in terms of how nitrous oxide is generated. And one thing that is very clear is that the amount of ammonium that is turned over per time per amount of bacteria or per volume is really one of the key numbers that we need to track. And I think we will see a correlation here between those. And that means, for example, that big plants that are loaded more and more as cities grow, they will likely have a higher problem with nitrous oxide compared to smaller plants that are not loaded that much and have capacity in treatment capacity as well, because hydraulic loads are actually fine on most plants with modern control, but then the treatment capacity might be challenged. But one thing that we actually could do was then to actually increase the amount of activated sludge in the tank, and this way we could dilute out the ammonium in the tanks, so that we actually decreased the load per bacteria, and that actually led to significant emission reductions, and overall over a period of a couple of years we have reduced around 65% compared to the baseline that Maria actually used for her LCA analysis. And the first reduction data that we had were the ones that went into the LCA analysis, and that was based on actually moving the bacteria to doing more simultaneous nitrification, denitrification by this decrease of the DO set point. And it is clear that if we have a higher DO set point and we turn over a lot of ammonium fast, then we will see higher emissions. There are a lot of other smart things we can do, and Anders have a lot of experience here as well. So maybe I can pass it on to you, Anders, to comment.
Well, yeah, thanks. What we see is exactly what you say, that the load of ammonia is clearly the driver for this. But I think it's interesting also to see that, and I don't think we can avoid to have that production of the nitrous oxide. But on our pilot plant, we have been experimenting a lot with adding also nitrous oxide and so on. So what we can see is that the emission is much slower than the denitrification. So if we can get the simultaneous denitrification to run, then, and of course that requires also to have more sludge in the tanks, and it requires a low DO set point, then we in fact can decrease the nitrous oxide, because it is simply denitrified before it can escape. So well, at least that's how we see it right now. But you never know. We are not that far, but that's our main result right now, and we can. And then of course, then what do we want to control after? And we can see that if we control after the nitrates, so saying that, well, we don't want to see a higher nitrate than this, so we have that as a control parameter. That's our set point. And then limit that so that we say that we don't want to have too much aeration going on still, so that we also look at our ammonia. Then at the same time looking at the nitrate, then we in fact can get quite a stable control that in minimizing the nitrous oxide. So
Dennis, you want to comment on that?
I think that's just challenge you a little bit, because when you talk about simultaneous nitrification, denitrification, I would claim that you don't use the volume as efficiently as if you do split up in processes. You also showed that EO is plug flow, so I'm curious whether you have a definite higher ammonia load in the first tank than in the fourth tank, I guess, and then you must see more N2O production in tank 1 compared to, I think it was the other way that was numbered, but the first tank receiving water must have a much higher N2O. And how do you deal with that then?
Well, we're doing that by limiting the amount that we in fact are degrading in the first tank where it's coming in. So we are trying to, with our set point, we have a dynamic set point for both ammonia and nitrate, and by having that, we divide the work so that it's going on in all 4 tanks. And as we have sensors in all tanks, also nitrous oxide sensors, we think, well, we can see how much each tank are doing of nitrification, denitrification, and so on. And then, of course, we have increased our suspended solids content.
And so it's very important for people who have plug flow plants to know that, because I think the traditional way of operating plug flow is to have a massive aeration in the first tank to cope with the incoming nitrogen, and that's actually very bad for the nitrous oxide production.
Yeah, it is.
Indeed. Yeah, it's a very good practical comment. Yeah.
You can, but in fact you can also in the first tank. We did see that, but that was mostly during winter. We could see that the denitrification, as long as we have enough sludge in the tank, then we could in fact load the tank much more, the first incoming tank there, to have the simultaneous nitrification, denitrification going on. So, and if we try to, then we limit the process at a certain stage, so that, and that we are doing with the threshold value on the nitrate, saying that, well, if we are getting too much nitrate, that's because we cannot denitrify anymore. So, and that, so the nitrification, denitrification, in fact, have different rates during daytime and nighttime.
Okay. Yeah. So with this dive into process control, maybe we can also think ahead into the future. Where you think, well, what are still the gaps in reducing nitrous oxide? What is still needed, and maybe what do you think will be the main maybe technology advances or process control advances that will help reduce nitrous oxide widely? I mean, of course, we have some very advanced treatment plants here with very advanced process controls and dedicated people. But yeah, what do we think? What will drive this from a process perspective on a broader scale? Does anyone want to volunteer on that?
Well, if I can say something from the LCA perspective as such, I mean, the carbon footprint, what I noticed when I performed all these assessments is that sometimes really the first step is to quantify this emission, but of course you need some kind of drivers. And yeah, I also agree with Dines that maybe a carbon tax could be a solution. And also we know that in 2025, the government is going to enforce limit values for N2O. So this is actually a big driver, because it's both the legislation, but also a tax that it's going to be a reality. We don't know yet if this tax is going to be implemented at wastewater treatment plants, but for sure there are going to, limits for N2O emissions are going to be implemented by 2025 for plants above 30,000 PE, if I'm not wrong. So it is actually a big driver in my perspective. And then if I may add, I see that wastewater operators are very ambitious in terms of their strategies, and also by setting up some goals for your organization. Where do you wanna where do you wanna be in 5 years, in 10 years? Do you want to contribute to this agenda or not? That is also a big thing, because the customers, so the clients, are also aware of the climate perspective. So at some point they might also ask for quantifications, and how do you quantify these emissions? What are your quantifications based on? So a big step is to really quantify it, and rather than relying on emission factors, standard emission factors.
Yeah,
that's my
and we had this.
point of view.
One very inspiring quote from one of our customers was, "We want to start doing this because we know it's the right thing to do." So that's goes along those lines. But then, of course, when it's more institutionalized, it will spread. It will spread much wider. Yeah. Mikkel, did you want to comment on that?
Yeah, it was just following up on Maria, because what is also important, and I think that is part of the presentation that Dines made, that we actually need to get more denitrification going in the rest of Europe, because if we let untreated or semi-treated wastewater out, then we will have the emissions of nitrous oxide being made in the recipients instead. So I think that is one implementation that is really important. But another thing that's also important is that will drive actually denitrification. So that will drive that we get denitrification going, and what Anna said is that denitrification is a very efficient sink for nitrous oxide. So once we have these plants doing more of this, then we would expect to see lower emissions overall as well. There is also the side of the energy and the biogas that Maria also has as part of her life cycle assessment, is that some of that carbon that we make green energy from, we actually might have to use that smarter in the denitrification, rather than making or competing with other green technologies for power generation at the wastewater treatment plant. So nitrous oxide is sort of the pivot in terms of balancing between green energy, which will of course defer some carbon emissions elsewhere, and then the scope 1 emissions on the wastewater treatment plant. So I think that will be a sort of a new focal point for at least the scope 1, 2 emissions in the water sector.
I have here two quite specific process-related questions that I would like to, from the chat, that I would like to just direct. So first one would be for Anas. For simultaneous nitrification, denitrification, it is probably much more important to be aware of your mixing and local conditions. Is that correct? And can you maybe elaborate on that? I understand the mixing is mainly done with the aeration itself.
No. We're not well, and that's the problem in some countries, that you are using the aeration for mixing, because then of course you cannot turn down your aeration. You need to have mixers, and you need to have controllable blowers. Otherwise, you cannot have simultaneous nitrification, denitrification. So
yeah, it takes a very well-equipped plant to run. Yeah, that's what we can say, I think.
So if you have plants which are very common around the world, where you're just doing nitrification and you're just using your blowers, and they might not be that controllable, and they're far too big always, and they're used for mixing the sludge and so on, then you really have a problem with your gear before you can go into really controlling your aeration. You need to install smaller blowers, smaller controllable blowers, and mixers.
Yep, that makes good sense. And then the next question would be for Mikkel on the increasing the sludge quantity. Maybe you can elaborate a little bit. It is understood here in the question that by means of MLSS increasing, and commenting on the settlability at the end, solids loading and the clarifiers. Of course, that has plant-wide impacts. So first to you, what you did actually process-wise, and then to finalize the question, what would Maria think about in terms of LCA when you look at settlers?
Yeah, so first of all, of course, it's mixed liquor SS that we are controlling. So we're increasing by half or 1 gram per liter in the case of Biofos, the plant. And in terms of mitigation, in terms of settability, we actually tracked that to the best that we could during the period, and we didn't see a large change in the settability during the process. There are some deviations, but the sampling spacing was a bit too wide due to COVID while we were doing this. But in terms of the operators, there were no problems with rising sludge in the clarifiers during the time. And we did this at this particular plant. We have high emissions in the spring and early summer, so it's not the wet season at all. So it was a risk that was monitored, but it was not an issue during the test. And in general, we haven't seen settability problems in what I have been involved with, but it is of course something to watch out for and monitor.
I might add that we don't see any change in our SVI according to running at lower oxygen concentrations.
Okay.
Yeah, I mean, what I can add in terms of the LCA, as I said in the presentation, all the LCA assessments should be based on mass balance and energy balances. So when you change something in your system, that can be, for example, introducing your prefiltrations rather than a primary clarification, and you are changing some kind of mass balance in the system and the substance flow, then in principle you have to rerun. And so I mean, I don't know what to say. I mean, what to tell you to tell now if this might increase or decrease the impacts. This should be based on assessment, and typically we trust experts who have done this analysis. And yeah, if the wastewater operators they make these balances and they figure out that the balance is fine, then we do not have yeah, any new input to the LCA.
Yeah, and of course we're working with the infrastructure that is there always in the constraints that are there. We are almost at the end of the time, and there's a lot of questions in the chat. I would invite you all to directly address the speakers with questions if you have one for specific people by emails. Yeah, here I would just like one last question, because I saw it very early in the chat coming up, and I think it's an interesting one to share. Just if anyone volunteers to explain what the situation is in Denmark in terms of carbon tax and the plan of nitrous oxide reduction from the legislative side of things. I would think, Dinas, maybe you have a good overview on that. Maybe you could take that part.
Only because I spoke to a guy from the Ministry of Environment recently. They're still working on how to do it, but I think what they are thinking of right now is actually the tax of carbon, that they will spread it out on the nitrous oxide as well. So if we get 750 kroner, that's about 100 euros per ton of CO2. That's the thought now. And if you add up what is the worth of nitrous oxide, and you can calculate how much is that per ton nitrous oxide. That's a lot of money. So I think that is going to be the legislation in 2 years in Denmark that we actually have to evaluate. We need a baseline of some kind. What is the where are we with nitrous oxide on a standard basis, and how much can we do? I think it's going to be coupled with a demand to lower your emissions by 50%. But of course, you need a baseline of some kind. I don't know if that baseline is going to be a standard national baseline, or depending on what you've been doing recently in the plant. But I guess it has to be some kind of baseline nationally. Like now we are saying that is it 0.8% of the incoming nitrogen is going to be transformed to nitrous oxide, and it could be a kind of baseline. If you can reduce that 50%, then you're okay. But at the same time, you get this 100 euros per ton. I think that's what we're going to see, at least what they're planning now.
Yeah. So that would be using the emission factor that was determined by the EPA project a couple of years ago. right? The national emission
Yes,
factor.
that's exactly.
Yeah, I think we will probably see similar things happening in other countries. Yeah, it's good to have an eye on that. Yeah, we have come to the end of the presentation or of our whole session. So yeah, you can of course direct questions to the speakers. We will also try to answer some more generic questions. We can try in our newsletter that is going out. But yeah, for now, I would just like to really thank all the speakers today for taking the time in the session, but of course preparing all the slides. We know how much work this was and how busy you all are. So thanks so much for doing this. Yeah, thanks to all the audience for being here today, of course. Feel free to connect with us, with the speakers, with ourselves at the upcoming shows, of course, as well. And yeah, very much looking forward to interact in the future.